We welcome you today to today's webinar, where my colleagues and I will introduce how the ArcGIS ecosystem supports meteorological data, visualization, and analysis using a fully web-enabled GIS. Thank you for joining us today. Meteorological information and mapping are applied far beyond weather forecasts. Businesses, government agencies, and individuals rely on weather and climate information to drive economic growth, protect lives and property, and support data-driven decisions. Today, we will showcase the advances we have made in ArcGIS to visualize and analyze meteorological data, which are essentially multi-dimensional data with dimensions like time, pressure, and altitude, thus creating unique visualization and analysis challenges. ArcGIS has the tools to visualize this complex data to help you see patterns and trends and find anomalies through maps, charts, animations, and powerful 3D views, as you will see in the technical portion of our webinar. This webinar is the first in a 5-part series on applied meteorology using ArcGIS. The titles and dates of the next 4 webinars in this series are presented here. This series takes you on a journey to see how ArcGIS advances the understanding of the atmosphere to benefit both science and society. We welcome you to come along with us on this journey. We also welcome your feedback at this email address here. Hello, my name is Lorraine. I am the Director of Earth Sciences Solutions at Esri, focused on geospatial technology for Earth Sciences applications. I am joined today by Jeff Donzie, who leads our weather and climate community efforts, as well as manage our relationship with the NOAA National Weather Service. We also have Lu Zhang, an Esri solution engineer supporting multi-dimensional analysis with a concentration in atmospheric sciences. And we also have Dr. Aiden, a senior researcher here at Esri on the spatial statistics and science teams, also with an extensive background on Earth systems applications. Today's webinar will be recorded and made available for future viewings. We will keep you on mute during this session, but I encourage you to drop your questions or comments in the chat at any time throughout the presentation. We will take time at the end to address your questions. We will also take the opportunity to engage with you in 2 polls to understand some of your interest in this field. We will have the first poll, and then we will turn it over to Jeff.
Thanks, Lorraine, and thank you all for participating in the poll. I also wanted to thank you for attending today and letting you know that how Esri has been working very actively over the past few years to support the weather and climate community to ensure that our products and services support atmospheric sciences, applications, and operations. You can kind of think of ArcGIS as a framework for applying science, mapping, and analytics to address the demand for weather information and products. As you can see by the examples on this slide, there are a wide range of use cases and organizations utilizing ArcGIS. For example, NASA's Atmospheric Sciences Data Center, which leverages GIS for the processing, archival, and distribution of NASA data, as well as meteorological agencies around the world like NOAA's National Weather Service, the UK Met Office, Australian Bureau of Meteorology, and others that are working with ArcGIS to provide access to critical weather information products. In addition, Esri has business partners in this community like DTN, AccuWeather, Spire, the Weather Company, and others that further contribute to this community by providing solutions built on Esri's framework for meteorology. Esri envisions our role as a special opportunity to connect both the producers of weather information and our users across a diverse and wide range of sectors, as you can see here in the slide. For example, you may be working with an emergency management agency with needs to track real-time events like hurricanes or floods to provide warnings to the public, or for an agriculture organization that needs to plan on impacts of severe drought on crops, more in sort of a climate analysis. The Esri framework can enable that collaboration between these sectors and meteorological agencies that are serving these critical data. Esri's own organizational structure provides us the ability to establish that connection between the primary consumers of the weather and climate information in meteorological agencies. Our teams are aligned to many sectors, many represented on this slide, from utilities to public safety to the insurance sector, to name a few, and ensuring the requirements for the location analytics are met, including the incorporation of weather and climate data. In addition, Esri continues to expand our big data management, analysis, and dissemination capabilities that are going to be increasingly important to meteorological agencies and consumers of weather and climate data, which we will highlight in more detail on May 12th during the third webinar in this series. Many of you may not realize that Esri also provides access to a wide range of curated global atmospheric data and content that you can find in our ArcGIS Living Atlas of the World. You can see the link up there on the top of the slide. This is the foremost collection of global geographic content available. It includes thousands of data sets in GIS-ready format, maps, apps, but also authoritative sources from thousands of contributors such as the National Weather Service, NASA, USGS, the European Environment Agency, and many others. We would also welcome additional data to be contributed by your organizations if you feel your data can benefit other organizations. The ArcGIS Living Atlas of the World is just another way that we provide that connection between the producers of weather data and the end user communities that require that data. Specifically for the weather and climate community, we have a series of core services in the Living Atlas of the World and apps that help companies monitor severe weather events, changing patterns in climate, that in turn help them to assess, detect, predict, and quantify the impact of climate change on their businesses, determine the specific risks to their operations and supply chains, relocate coastal assets, find alternative supplies or delivery services, uncover stranded assets, and alter their business plans accordingly. Commercial weather agencies use these Esri apps or custom apps built with our technology to provide climate forecasts as GIS ready for their use by their customers for the aforementioned purposes. Now, to show you more on how you can work with meteorological data in ArcGIS, I will turn it over to Lou, who will demonstrate these capabilities for you. Lou?
Awesome. Thank you, Jeff. Go ahead and share my screen. So while in doing so, I'm going to take the next 10 or so minutes to show you the fundamentals of working with multi-dimensional data using our ArcGIS technology. Then I'm going to pass it over to Orrin, who's going to show you some more advanced and cooler workflows using our tools. So before we get started with the demo, we may need some data. And this is where we can turn to NOAA's repository of gridded climate data sets. If you take a look at this repository, it contains a variety of different climate and weather metrics, ranging from soil moisture to temperature to precipitation. So we can browse this website and choose a data set that we might be interested in. So in this case, it's the University of Delaware precipitation and air temperature data set. contains values for over 100 years worth of data in monthly terms. How do we download this data set? We can choose here. And as you can see, the format is in a multi-dimensional NetCDF format. So with ArcGIS, the fundamentals is that if you have the data, we can ingest it. So I am currently in ArcGIS Pro version 2.6. And if I wanted to bring in the data set I just downloaded, I'm going to click on this GUI right here to add in my multi-dimensional raster data. From here, I'll go ahead and point to the data, which I have stored in my File Explorer, which I just downloaded. And here I can take a look at the variables that's contained within this NetCDF file, which in this case contains 1400 months corresponding to 120 years worth of temperature data. So once ingested, in this case, we're going to take a look at precipitation from that same source. This is how it looks like once it's ingested, and you can kind of see that this data set covers the whole globe. And I know that it's multidimensional because I have this multidimensional tab right here, and this gives me context to the nature of my data. By clicking on this tab, I can see the different functionalities that I have with regards to analyzing this data set. Currently, the time is pointed to January 1929, but I can go ahead and point towards any other year and get the pixel value for that specific time, but also a specific location. So in this case, the precipitation is 12 centimeters. Now, multi-dimensional raster layer is also a raster layer, so I can also perform raster functions on top of this data set as well. So the first thing I might want to do is to interpolate the data. This data set is 1/2 degree by 1/2 degree. In order to get a smoother surface, I can interpolate it with each location to its surrounding cells. So now I can get a smoother value from my data for me to analyze. And now, once my data is ingested, I can start doing some analysis. So I'm going to go back to my multi-dimensional tab and take a look at the different tools that are available to me. Some sample tools, including zonal statistics, allows me to run general summary statistics on different polygon regions that I have. But the next thing I want to do, naturally, is to create that base period. So in this case, I might want to use the subset multi-dimensional tool. So I can create a base time period in order for me to calculate different metrics such as anomalies, as well as long-term averages. So I'm going to point towards my multi-dimensional raster that I just ingested. And from here, I can set the different ranges where I can go ahead and subset my multi-dimensional raster layer. And once done so, I can now create a general product. And this could include trend. So if I wanted to calculate long-term trends based off of the subset of the multi-dimensional data that I just did, I can go ahead and run this tool and determine the trend type that I want to calculate. I can also run some additional statistics as well to get a general fit of my data. And here's the results of this tool. And if I turn on the legend, I can see that green values indicate that this area has been getting drier, whereas purple values indicates that areas have been getting wetter over the past 100 years. Now, since this is a global data set, I can pan around the world within my GIS environment and see some interesting patterns, especially over sub-Saharan Africa, where we can see that precipitation has substantially been getting lower over the past 100 years as a result of expanded desertification of the Saharan desert. And to verify these trends, I can unlock some additional tools. One of these tools is that I'm going to start creating a space-time cube from my weather data, from my precipitation data. In case you're not familiar with the space-time cube, it's kind of like a 3D histogram where you're going to bend together space, time, as well as space-time and so in this case, I can go ahead and bend across space and time to get different bends. And by creating a space-time cube, I can go ahead and visualize the trend, and this is what it's going to look like. And again, as you can see, areas in green indicate statistically significant decreases in precipitation, and areas in purple indicate statistically significant increases in precipitation. So I can go ahead and click on a bin over this sub-Saharan region and take a look at the long-term trends, where it's going to sample my data set, but also run this test against the coefficients to determine exactly how significant this increase or decrease in trend is. So with that being said, here is a sample analysis where I can conduct in 2D. Let me go ahead and switch over into a 3D environment. So if you have the data, we can read it into an Arcgis environment. So in this case, we're going to take a look at California wildfires that occurred last year. So again, I'm going to go ahead and click the Add Data button. In this case, I want to take a look at my multidimensional data in a 3D environment, as well as animate over time. So I'm going to take a look at the AIRS data, which represents carbon monoxide values over all levels of the atmosphere. So by ingesting this data, I can choose the variables I want to ingest, and this is what it looks like. This is a voxel layer across all levels of the atmosphere that I can animate over time. So we'll start off over early September, and this is where the propagation of the California wildfires first started. So in order to see the highest concentration of wildfires, I can go ahead and change the transparency function. And again, to do so, I'm going to go ahead and go over to these contextual tabs that give me functionality for my specific data type. So I'm going to go ahead and click on symbology and set this transparency function to the right. So from here, I can go ahead and enable the transparency function and choose the range where I want to make transparent. So I'll go ahead and set a control point and leave everything else as transparent so that we can see the distribution of the smoke plumes of these California wildfires. So now I can animate this voxel layer throughout time, and you can kind of see the propagation of these plumes as I go ahead and move throughout time. And lastly, you might be wondering about the connection between my desktop GIS environment and an online GIS environment. Since we're using ArcGIS Pro, any layer that you publish, you can also share to your ArcGIS Online environment. And to do so, I can click on any layer that I just created and go ahead and share it as a web layer. And now I can give my data a title, along with some corresponding metadata, such as tags and summary, so that an online audience can take a look at my data set and continue my analysis. So with that being said, I'm going to briefly go through a browser-based environment to show you some additional analysis that you can do within an ArcGIS Online environment. So here's a notebook within my ArcGIS Online environment that's developed by a colleague. And since I am in an ArcGIS Online environment, I can go ahead and open his notebook and inspect his workflow. So we'll go ahead and continue our analysis on different wildfire events, and I can take a look at his workflow. In this case, we're looking at the ArcGIS API for Python, where we can conduct geospatial analysis using hosted data. So in my first two demos, I showed you analysis using local data I downloaded from NASA and NOAA. In this workflow, I'll show you analysis using data that's already hosted online. so I don't have to fill in my file explorer. So I can take a look at some digital globe imagery that's in the form of a tile layer. And using the ArcGIS API for Python, I can take a look at the side-by-side imagery of before the wildfire and after the wildfire. And to do some more further analysis, I can go ahead and bring in the hosted Landsat image service that we host within the Living Atlas of the world. And the reason we might want to do this analysis locally, in a hosted environment, is because Landsat imagery is really extensive, covers the whole globe over the past 50 years. Therefore, we really need to define our area of interest, which is our wildfire region, but also to define the exact image chip that we want to analyze. So by integrating the ArcGIS API for Python with open source pandas functions, we can kind of query our underlying data set through pandas data frame. So this kind of gives you an idea of how our large hosted data sets are being managed, where the metadata of each extent has a corresponding metadata, such as cloud cover, acquisition date, as well as the extent. So I can use pandas queries to filter by the exact time slice that I need, one for before the wildfire and one for after the wildfire. And by identifying these image layers, I can use out-of-the-box raster functions from the ArcGIS API for Python to calculate the difference. So in this case, we're taking near infrared bands for the pre-fire and the post-fire to calculate the difference. And here's the results that shows you the extent of the burn area for this wildfire. And furthermore, I can also sample out the pixels to get a general idea of the extent that's being burned. And if you have your own custom algorithms, you can actually export your data into a different file formats, such as TIFF, so you can perform your own custom analysis on the data sets themselves. And of course, since I'm working in an ArcGIS Online environment, I can go ahead and save this notebook as my own item. So I can go ahead and share out my workflow with my organization, as well as to the GIS community. So with that being said, let's go ahead and take a poll, and I'll go ahead and pass it over to Oren, who's going to show you some more advanced analytics within ArcGIS environment. Thank you.
Hello. In these demos, I will talk about applications of spatial and spatiotemporal data science to climate applications. The first problem that I will talk about is the climate downscaling problem. In particular, I will be talking about statistical downscaling, where the problem is posed as a regression problem, where we would like to relate large-scale global climate models that can model large-scale climate patterns with local observations of the impacts of climate, such as local temperature measurements. So using these 19 simulated variables, we would like to find a statistical relationship between these simulated variables and observed temperature. And this statistical model, this downscaling model, can be used to calibrate future projections of these simulations. And this also gives us some insight about the relationship between simulated variables and observed variables. Here, I'm showing you centroids of a global climate model. We know that this is a raster, but I just want to point at some of the scale disparities between the simulations which have centroids at these black points, and also temperature measurements which are depicted with these red points, with the legend as the temperature measured in the March of 2012 over the United States. Here I'm using a small subset of the data set that is available. And one thing I would like to mention before we start doing analysis is a very common problem. And that problem being having some station data missing. There can be many causes for this. The station might be down due to some electrical issue. And at some point in our analysis, we have to make a decision. We either discard all of the missing data points in space and time, or we fill them somehow. First, I will talk about this problem, this data imputation problem, which is a part of a bigger problem when we're doing analysis with climate data, that is wrangling this data, fixing this data. The first tool I will touch on that can solve this problem quite easily is fill missing values. This is a geoprocessing tool that can fill missing values in data, such as the -999s we looked at. Here, I'm asking the tool to fill every -999 with the median of the 10 nearest stations that have data. This might create over-smoothing in your data, but if keeping these data points is quite important, and knowing that there is a strong spatial autocorrelation to the observation, which is temperature measurements and solar radiation here, we can apply this method to fill in missing values prior to our analysis using a rigorous method. And this gets us to step one, that is filling in these missing values where we do not have them. So this gives us a map of which values were filled using their nearest neighbors. So we had a variety of stations that were missing in this area, in particular Colorado Plateau, that were filled by using its nearest neighbors. And after going through this initial step of data cleanup, let's talk about how we can create some of these simulations. So here I have filled station information, where I have filled temperature values, and I have simulated climate. I'm just going to clip the raster here, and I'm just going to show you only 2 rasters out of 19, such as airflow, sea level, pressure, and this is just a snapshot for March of 2012. So let's see if we can find a relationship between these using statistical data science methods. I will talk about a variety of methods, and let me go to the very first method that I've tried here, which is a support vector machine regressor. For those of you who use ArcGIS Pro in your analysis, one question you might have is, I've never seen the support vector machine regressor tool before. I know about the raster tool, but I've never seen this tool before. Is this a new tool? Actually, what I did here is, using a popular machine learning library that is scikit-learn, I created, using our script tool integration, a ArcGIS Pro tool myself, and you can do this quite easily yourself as well, that just calls scikit-learn in the background to do support vector machine regressor and also ridge regression. Because using this method, I can leverage open source libraries to do analysis in ArcGIS Pro, and I will compare outputs from some of these non-spatial machine learning models to spatial machine learning methods that we have available in ArcGIS Pro. Before talking about the regression results, let's summarize the data set. One thing I've done in the background is, at every temperature location, I've extracted the simulated values. And one thing you might be wondering, what are the relationships like? Using our charting capabilities in ArcGIS Pro, I can actually investigate and create this scatter plot matrix that summarizes relationships between different variables. This is quite important because if you're going to use a linear model, you may want to make sure that there is no multicollinearity, or overall, you may just want to understand the types of relationships, the strength of linear relationships between your variables, or simply clicking on these boxes, such as this box that corresponds to vorticity and sea level pressure to see what the relationship is like at this particular time slice. This plot is quite customizable, so if you would like to slice and dice your data and visualize it in different ways, we can also look at all the little histograms. We can fit linear trends so that we can understand whether there's a strong linear relationship between different variables, so on and so forth. After doing this initial investigation, some of the models that I will apply do not have a multicollinearity problem, such as the support vector machine. And when I apply this to data, and here what I mean apply this to data is forming a relationship between all these simulated climate variables and observed temperature. This is a prediction that I can create with the particular error penalty and the kernel that I defined. This is a great example of overfitting, which means that the model did a great job of explaining the temperature where the stations are, but it's not really performing that well anywhere else. Next, I will try a ridge regression, which gives me a handle for controlling this error penalty directly. When we look at the ridge regression result, which is again another method that I brought in from scikit-learn by creating this Python toolbox and relating all these variables, I see a more sensible prediction, downscaling result of temperature. Here I'm just looking at a coarser scale, but I can produce these results at a very fine scale given my climate simulations and my temperature locations and my temperature measurements. Next, I will try a non-spatial machine learning method, random forest, which is our own implementation. So this is not brought in from scikit-learn, but this is our very own implementation. And for this problem, I'm basically going to use all of the variables that are available to me, which are all these simulation variables, and I can easily add these. And once I form this model and this relationship, I see with random forest, I can actually capture some smaller scale variations in temperature in this downscaling result, which is quite useful. And also, this being a pro tool, it creates a lot of useful charts on the fly, such as variable importance, so that it tells me which variables are more impactful in predicting local temperature, and it gives me this idea. And also, it does create an uncertainty bound for my predictions, so that I have an idea of a P90 and a P10 bound on the predictions that I make using this tool. So this becomes particularly important when I'm working on a system where I know that there are many sources of uncertainty to it. Lastly, let's apply a simpler model, which is GWR, geographically weighted regression. So here, this is a linear model, a locally weighted linear model, where at every location, we'll be using a geographically weighted linear regression to create a prediction. One caveat of GWR is it's prone to multicollinearity, meaning that we cannot have variables that, once weighted at this local scale, cannot be linearly related. So here I picked 3 independent variables, also with the help of my scatter plot matrix, to create a prediction. And when I look at my GWR result, I can see that I can produce some of these overall patterns of temperature variation. This may not be as accurate as random forest. However, I can still create a smooth variation of temperatures using very small number of variables and modeling space explicitly at the algorithm level. After having taken a look at some of these functionalities in ArcGIS Pro, I would like to talk briefly about our R integration. It is quite interesting to see that there are actually a lot of you who are using R, and I would like to show you how you can leverage R alongside our JS functionality to enrich your ArcGIS workflows. In particular, I will be talking about our Arcgis Bridge, also known as ArcGIS Binding, which is the package name. This is a product that we serve that you can use alongside ArcGIS Pro and Desktop. This allows seamless data interoperability between ArcGIS and R, where you can take your spatial and spatiotemporal data sources, whether they are local, like shapefiles and rasters on your hard drive, or cloud-driven, such as image services and feature services. This brings you the power of seamlessly bringing them in as an R data frame to perform your analysis. And I will show you some of the integrations that we have enhanced with ArcGIS binding and other libraries such as Leaflet Esri, so that you can power these R notebooks, which is the notebook that we're looking at. This is quite similar to the notebooks that Lou showed you, but one difference being this R symbol here on the top right. So after we import all of our libraries, we run ArcCheck product. ArcGIS binding requires you to have ArcGIS Pro installed on this machine or ArcGIS desktop. And once this check is made, using our reticulate integration, I'm going to bring in ArcPy library. And if you're not familiar with ArcPy, ArcPy is our spatial data science library that derives the tools, geoprocessing tools in ArcGIS Pro. So this means that I can actually call Pythonic geoprocessing tools from this R notebook. And this gives me the ability to leverage ArcGIS and R inside an R notebook. The first thing I will do, and in this I will analyze temperature anomalies from a feature service, and this is a feature service that uses data from NOAA. So here I have these different measurements, and I have different years at the bottom that start at 1880 all the way to 2030 projections. So these are temperature anomalies that are recorded and after 2020 projected. I would like to bring this data set in, which lives in a REST API that looks like this in this URL. It's an R data frame so that I can analyze it. And we can do that with ArcGIS binding quite easily. All I need is the full URL to the REST API. And I can directly read this feature class in. And here you see all the columns associated with this feature class. And using ArcSelect, now it becomes an spatial R data frame. And at this point, we brought a cloud-driven database, spatial data, to R as a data frame. And this gives us the power to do analysis in R using this data frame. Another very useful functionality of our ArcGIS Bridge is creating interactive maps on the fly using Esri leaflets. Here, I wanted to embed a slice for 2020 temperature anomalies here onto this map, and I create some interactive statements here so that I can interact with this map in my notebook. And this becomes particularly useful if you're producing data products, because this is outputted as an HTML, if you would like to embed this in a widget, or if you're publishing a paper and you want an interactive component so that more dimensions in your data set can be sliced and diced with a supporting notebook, you can easily do that. I am going to be writing this data set that I obtained from the cloud into my local geodatabase as a feature class. And I can simply do that with ArcWrite. And we will use this feature class in a little bit. Going along in my R analysis, one thing I would like to understand are spatiotemporal patterns of these temperature anomalies since 1880 all the way to 2020. What I will do here is I will use an ArcPy tool, point to raster, which converts these points to rasters, so that I can run this in a loop to create a stack of rasters for all the years that I have temperature anomaly data. One thing I would like to do to make sure this works, after I run this ArcPy function that converts the point data set that we see here for temperature anomalies of 2020 into a raster, again, using our Esri leaflet integration, I can create an interactive raster of my output. So this is the raster for 1880 temperature anomalies. And now that I know this works, I'm just going to put this in a loop. I'm going to loop over from 1880 to 2020, run a geoprocessing tool to convert everything to rasters, and stack those rasters so that I can use a niche R library that creates Hovermiller plots. And that is the power of ArcGIS and R integration, where you can leverage general tools, analysis tools in ArcGIS Pro, alongside niche tools that exist in the R ecosystem. Here we can create Hovermiller plots using the output of the geoprocessing tool we just ran in a loop. So here we're looking at temperature anomalies from 1880 all the way to 2020. And here is the latitude so that we can actually see the wave effects. And we can do the same thing, same Hovermiller plot on the longitude as well, so that we can delineate some patterns of these temperature anomalies as they evolve over space and time. As I mentioned, We can write this data set seamlessly into ArcGIS Pro as a feature class. So here, the data set that we wrote from that R notebook was the temperature anomaly data set. And quickly, when we look at this data set, we see that the time dimension in this data set is captured in columns. In other words, different times are represented as different columns. But if you want this as a space-time row format, you can use a tool such as transpose to easily convert these columns into rows so that you can stack your data on time, create space-time cubes like Lou has shown in his demo, and using these space-time tools, using the space-time cube. So here I'm showing you how to basically take these columns and make them into rows so that you can create a space-time cube. You can do visualize 2D, explore some local patterns, interact with this map, look at the time series. You can also do predictions using time series forecast. Here I have done a decade log forecast of what the temperature anomaly is going to be like in the year 2040 using the data all the way up to 2030. We have tools such as exponential smoothing forecast, forest-based forecast that you can easily utilize as these tools. More importantly, and this is the last thing I would like to touch on, I can capture my entire analysis as a model, which is what we call model builder. I can capture my fill and missing data steps, my transpose field steps to prepare my data for analysis. I can capture my space-time representation steps by creating a space-time cube. And I can capture this entire workflow that ends with autoregressive forecasts and space-time pattern visualizations. And if you have a different data set, and if more data set comes in, you would like to go through this sophisticated workflow over and over again, you can easily run this entire model that'll start at raw data and end with analysis results. With that being said, I would like to pass the mic back to Lorraine.
Oh, hold on, folks. We'll just get this in slide mode. There we go. In today's webinar, we have shown you both straightforward and advanced visualization and analysis workflows that help you to make the most of your weather and climate data. You saw how ArcGIS can seamlessly connect to a large variety of meteorological data sources, removing the burden of learning how to connect to different types of cloud sources. For those comfortable in the scripting environment, we hope that you enjoyed the demonstrations on how Python notebooks, ArcGIS API for Python, and R make it easy to integrate GIS into common weather and climate applications. We will now take a few questions that have been coming through the chat. If those still on the call, if you have any additional questions, please add those as well. If we don't get a chance to answer all the questions, we will make those available in the follow-up email, which will also contain links to resources on this topic, including a complimentary Learn lesson that will help you further enhance your skills. So I'll be getting my teammates to help with these questions. So the first one I have is there a training that I can take to learn how to bring in weather and climate data to do time series analysis? And so, yes, there's lots of training available. And again, we'll make this available in the resource section. And even for those of you that have seen this demo today by Dr. Aiden, he has produced a whole Learn lesson that is complimentary for anybody to take on many of the analysis that he presented today. So we'll be providing that link. And maybe for either Lou or Aiden, if they could comment on, is it difficult to learn how to work with R and ArcGIS?
I can comment on R and ArcGIS portion. It definitely it's not a very steep learning curve, and especially if you have some R knowledge. ArcGIS binding, which is the Arcgis Bridge, is an R package that we develop, and it basically works exactly like any other R package. So it's quite seamless in terms of using it, and we such as reaching data sources and representing spatial data in R. All those steps are handled in the background so that you don't have to worry about those nitty-gritty details of how to manage your spatial data in R as well.
Thank you. We also had questions about how do I find the notebooks that both Lou and Aiden showed today. Can both of you guys comment on that?
Hey, sure, yeah. So in addition to the resources that, our team has composited, I will be making sure to share my data sets, the workflows, the notebooks as a follow-on.
Yeah,
Great.
that's exactly the same for the R notebook. I'll make sure that the team has it, and then they will be shared out with all of you with all the other relevant resources.
Okay, and so that actually answers another question that we had. Well, actually not exactly, but it says, how can I share my analysis results with others? Within those notebooks, there's opportunity to do that, but maybe you guys can comment on that as well.
So if you would like to share analysis, having it in a notebook format is the easiest format. And currently, you can easily share our notebook with anyone. These are portable notebooks. In terms of data products, if you're creating data products, it might be a good idea to basically either use Hub or simply just put them as cloud-based feature services and image services within your organization, so that other people who are working on similar problems who might need these data sources can seamlessly access them without requiring data from a hard drive.
Okay, one more question. Where do I register for additional webinars? I believe Noelle is going to drop the link in the chat. And for those that are not available or online, we will also have that information available in the follow-up email. So we hope that you have found today's session informative. Feel free to reach out to us at this email on the screen. Many of us on this call and others are monitoring that email, so we're happy to hear your feedback, ideas, and suggestions.
Lorraine, I might add,
Yes?
I don't know if we want to try to look, there are many more questions into the question area.
Could you take those then, Jeff? I'm not seeing those.
Okay, let's see if I can get a few of those anyway that we can respond to. And if we don't get to all of your questions, we will respond after the event. If I'm using the data from Living Atlas and Esri web maps, is there a way to have that data update automatically, even with the refresh interval set correctly? The data doesn't update unless the web page itself gets refreshed or the map is panned. I don't know if Lou or Warren, if you could take that.
I would recommend taking a look at streaming layers, because these streaming layers can stream data on the fly, so it might solve some of these latency issues. And we definitely have support for in-time features. Actually, in my demo, the NOAA data that I showed you is being updated regularly every month. So if you ran this notebook next month, you will have yet another data point to process. So on the background, updates are happening, but if you're having some latency issues in terms of looking at your data, I will definitely recommend taking a look at streaming layers.
And I would just add on one more comment. The Living Atlas, some of the services are indeed live, such as, live watches in the mornings. However, if you want to update your own data layers, using the ArcGIS API for Python, we have functions that allows you to update your different features through REST. So therefore, you can schedule your notebooks so that the maps that you're creating are consistently updated with the latest features and attributes.
Okay, thanks. Another question, are multidimensional data and tools available only for ArcGIS Pro? Lou?
Hey, that's a good question. I might need to get back to you on that because I am not aware of the extent for support in ArcMap, but I can tell you that all the newest tools with regards to multidimensional data and analysis will be only exclusively added to ArcGIS Pro.
Thanks. Another question, are there any plans to include more granular weather data for Europe and UK in the Living Atlas, specifically data that can be queried against critical infrastructure assets in real time? I do know we have support for some of the Sentinel data that I think is fairly popular in terms of working with in Europe, but I can't, and then in terms of applying to your infrastructure data, there are other Living Atlas data sets that you may be able to find that might have infrastructure data, or certainly there are a wide range of demographic data sets that are available globally. I know that isn't specifically infrastructure, but you can certainly combine those data in your analytics. Another question, how do you clip a multidimensional raster using a shapefile to just clip your area of interest? Lou, do you know that? Lou or Oren?
Hey, yes. I would think that a simple clip raster tool will work on a multidimensional raster, as in the output will still be a multidimensional raster CRF file. But I will double check on the tool documentation to verify if the clip raster tool will work on a multidimensional raster while preserving all of the time and variable components.
Another question I think we have addressed, but just to make sure it's repeated, will a recording of this presentation be made available? And yes, we will be providing a recording afterwards. And somebody said this is outstanding information. We hope that's the case and appreciate your giving us that feedback. Let's see if we have any more. Let's see. Filling station data, sorry, I'm having a hard time reading this. Filling station data gaps are easy for temperature. How about precipitation? Oran, do you know that?
Yeah, so it depends on if the question is alluding to a niche model that is used for imputing precipitation values, that can be integrated through Python or R. But if you would like to use the same process, our fill missing values works on a variety of data sources. And again, you can follow the exact same workflow like I did, just using the fill missing values. And if you would like to fill using spatial neighbors, you can basically just use that tool on precipitation the same way.
Okay, thanks. And will some of the notebooks that you all showed, will they be available publicly?
Yes.
And how do they gain access to those?
I believe they will be a part of an email that they will receive. I'll make sure that those are available.
Yes, that's correct.
Great. Is an ArcGIS subscription needed for use of the Python API library? I think we'll have to follow up with an answer to that question.
I can quickly answer that.
Okay.
Actually, you don't need. So the ArcGIS API for Python is a collection of Python modules that replicates WebGIS functionality. So just as WebGIS, you don't need an explicit subscription, right, account to access ArcGIS Online. So certain functionality of the ArcGIS API for Python will be available without any subscription. although other more advanced functionalities will require you to authenticate to your Arcgis Online account.
Okay, thanks. Thanks, Lou. Why was one of the analysis outputs expressed with time on the y-axis and latitude on the x-axis, as opposed to the inverse?
So this is that is the Hovermiller diagram. So that is basically one way of representing spatiotemporal patterns in climate data, and that basically that might be an artifact of the package I used.
Oh, okay. Thanks, Warren. Another one here. I believe R and Python packages are built. Sorry, I had to jump ahead. I believe R and Python. Oh, I'm sorry. Somebody did answer a question. I apologize. That was an answer.
How about this one? Is it possible to create CRF from a time series vector data? If the data format is in shape time series, how may I create a multi-dimensional raster data set? Ooh, that's a complex one.
Actually, part of that you can also find in the climate downscaling learn lesson that I believe the team will share after this call. I think there are different ways of doing it. One way of doing it is creating a time-enabled mosaic from your vector data.
Okay, thanks. I have another one. Can ArcGIS Pro be used to build cubes of different files?
If I understand it correctly, the question is asking for if ArcGIS can be used to create space-time cubes for different types of variables.
Yes.
If that is the case, yes, it can be. And you can, if it's the same spatiotemporal resolution, like if the space-time bins are the same, location and time-wise, you can store multiple variables in the same space-time cube as well.
Okay, last question maybe, Jeff?
Okay. Let's see, I think you answered the CRF question. Let's see, here we go. Was that notebook not a Jupyter notebook, but rather an R notebook? And we're referring to the temperature anomaly study with R. Was that notebook not a Jupyter notebook, but rather an R notebook?
It is a Jupyter notebook. R notebooks and Jupyter notebooks are used interchangeably because, as you know, Jupyter stands for Julia, Python, and R. So yeah, it was a Jupyter notebook.
Okay. Well, there's several other questions that we'll work to try to respond to for those that have asked the question. I'll turn it back over to you, Lorraine, to close out.
Okay, close it, yeah. Well, thank you so much for inputting your questions. It's great to see some interaction with you. And like Jeff said, we will, whatever questions we didn't get to today, we will make sure they are answered and we provide those answers to the whole team. Again, we hope that you found today's session to be informative. We always welcome your feedback at this email address. Feel free to reach out to us at any time. We thank you for joining, and we invite you to attend these additional webinars in this series. So this now concludes our broadcast.